Welcome to Weighing, Measuring, and Making Solutions by Amino Labs. In part 2, we're going to look at the fundamentals and the computations of concentrations. Concentrations involve quantifying the amount of things in a volume of liquid. And this is deliberately vague because there are several different ways to describe concentrations in the lab, and there are a lot of things that can be quantified within a volume of liquid. So in this section, we're going to be going through 5 different ways that concentrations are quantified. A couple of these are used heavily in the lab, some of them are not, but it's important that you know them all. So the 5 main ways are percent weight concentration, where you have a percentage mass of a solid, such as a sugar, dissolved into a volume of liquid. And this is identified by the percent W/V designation. You might have seen this on a product you bought from the store. It's not so widely used in the lab, but if you see it in the lab, you'll know what it means. The second is the percent volume concentration. So this is like above, except rather than a mass in a liquid, it's a volume of another liquid in a volume of liquid, all right? So you could have vinegar in water as an example, and this is identified as the percent V/V. So again, like above, you might have seen this in the store, or maybe you have contacts and you saw this on the wash solution for contacts. Something like that. So this also is not widely used in the lab, but if you do see it in the rare instance, you'll know what this means. The third is mass concentration, and this is where you have a mass of a solid, such as glucose, dissolved into a volume of liquid. And the difference between number 3 here and 1 is that we're not looking at percentages. We're looking at more absolute units here. So we have, for example, a mass in grams over a volume in liters, right? And you can have different units here, milligrams per microliter, milligrams per liter. But the important thing is that we're looking at a very specific mass over volume, no percentage here. And this is very widely used in labs, and so it's good to get a handle on this one. The fourth one here is molar concentration, and this describes the number of molecules in a volume of liquid rather than looking at the mass, all right? And the example unit is moles per liter, right? This one is probably going to be the heaviest subject we cover here. So take your time on this one. Make sure you digest it. If you need to go back and go through this, please do. Molar concentrations are generally university level concepts. And so it's good on you for jumping through this and learning it. If you're in high school, it's a big accomplishment. Molar concentrations are perhaps the most widely used measure of concentration in the life sciences. And so if you can get a handle on this one, you're going to be set up. And then the last is dilution concentration, which is quite simple once we've gone through the rest of these. The basic idea is you have a highly concentrated liquid that needs to be added to another liquid to get the right concentration. So you dilute a predetermined and known highly concentrated liquid into another. And so, for example, you might need to dilute 1,000 times into another volume. And this is pretty widely used in labs, but as you'll see, it's pretty simple once we've gone through these others. All right, so the first two here, we've got percent weight and percent volume concentrations. So we got the percent W/V and percent V/V. Again, these aren't widely used in labs, but you'll see them in stores, on products, and there will be a rare instance where you do see these in the lab. And you'll actually be able to, once we go through the next topics, you could technically find the mass, volume, and even the molar concentration of these if you needed to. So it's a bit antiquated, but we're going to go through it anyway. So typically these are, whether it's weight or volume, we're looking at a volume that is usually over 100. Okay, so when we think about percentages, usually it's over 100, right? So 1 over 100 is 1%. So within these two measures, we have a volume of, let's say, 100 milliliters. And so we would have grams per 100 milliliters, or milliliters per 100 milliliters. And this is pretty important. And so just to give a couple examples here, if you have 5 grams of sugar in 100 milliliters of water, your concentration would be 5% weight per volume of sugar. Okay? If you had 5 milliliters of vinegar in 100 milliliters of water, you would have 5% V/V, volume vinegar. Okay? And that's simply by dividing 5 over 100 and timesing by 100%. So again, rarely used in a lab. Remember that these are always a volume of, you need to get to 100. And so you don't need to always have 100 milliliters. You can have less, but when you're calculating the percent, you need to modify your system so that the denominator is 100. So for example, if you had 2 grams of powder and 25 milliliters of water, that would be 8% weight per volume. Okay, and you do this by, this 25 needs to become 100, right? So you would times that by 4, and therefore you also need to times the numerator by 4, which would get you to 8, and therefore we would have 8 over 100 is 8%. Okay. This is also a little antiquated because we're using weight, and you'll see this a little bit throughout this whole section. Weight is an outdated term. Mass is much more precise. Weight it works on Earth because weight and mass are equivalent under 1 g of acceleration due to the Earth. So technically mass is a better word to use, okay? But they're sort of interchangeable. So here's just 2 examples of how you would calculate. So we've got, again, you've got a weight or a volume that's over 100 milliliters, for example. It could be in ounces. You could have various other units, but it would be very common to have grams or milliliters over milliliters. You times that by 100%, and that gives you your concentration. So for example, 25 grams of sugar over 100 mils of water, that's 0.25, times 100% gives us 25% weight per volume of sugar. 15 milliliters of vinegar over 100 mils of water, so that's going to be 0.15 times 100% gives us 15% volume per volume of vinegar. All right, on to section 3, mass concentration. So mass concentration is very widely used in the lab, and it involves taking a solid that is to be dissolved in a liquid. This is called the solute. It's a very important term. And dissolving that, mixing it and dissolving it into a solvent, which is the liquid that the solid, solute, is to be dissolved in. And this could be something like water. When you mix the solute and the solvent together and they mix well and the solid or the solute dissolves, you get a solution, which is the liquid solid mixture. Okay, and so if the solute is glucose sugar and the solvent is water, your solution could be sugar water. Okay, so again, very widely used in labs, used on a daily basis, and it's a very simple calculation, right? So it involves dividing a mass into a volume of liquid, and then generally converting that value into a prefix unit volume that's more easy to work with and easier to read and understand. And we'll do some examples so you see what I'm talking about. So in short, we've got concentration, big C, equals mass of the solute, so that's the solid, which is a small m, divided by volume, which is the solvent, so divided by big V, right? On the right, we have a super simple example where we have a mass per volume in grams per liter. And this can be the case if you've got, let's say, 5 grams of sugar in 1 liter of water. Your concentration would be 5 grams per liter. All right, let's look at a little bit of a use case here. Let's start by dividing a mass into a volume of liquid, and then we'll modify the prefix unit volume so that it's a little easier to work with. So the use case is you need to make some LB agar plates, which you've done in the past, although you may have used pre-mixed, pre-prepared tubes of powders and whatnot. So in this case, you need to make some LB agar plates to grow some bacteria on. Your recipe says, using a weigh scale, measure 4 grams of LB agar powder, that's the solute. Using a beaker or graduated cylinder, measure about 100 milliliters of water. Pour the LB agar powder into the water, heat to mix and dissolve the LB agar, and pour your plates. Okay. If we were to look at the mass concentration here, we took 4 grams of LB agar, and we put that into a total volume of 100 milliliters of water. If we run that calculation and just go straight over with these units that we're using, we would have 0.04 grams per milliliter. Okay. Now, grams per milliliter is a very strange unit to use. This would almost never be used in a lab. So this is where we get to the second step here, where we're going to just convert these using our new knowledge of, or past knowledge of, prefixes. And we're going to make this a little more easy for someone to understand. Okay. So let's pop to the right side here, where we've got 0.04 grams per milliliter. And we can convert that to 40 grams per liter. All right. And we do this by, you can see here, we're converting milliliters to liters. So that's a 1,000-fold increase in volume. And so we also multiply this by 1,000. So move it over 3 decimal places and we get 40. Okay. So this is a much more widely used unit, grams per liter. It's used a lot. And in fact, if you were to go online right now and look for some LB agar and the manufacturer's instructions that come with them, they'll likely be using grams per liter. Okay. In this case, they'll probably even say use about 40 grams per liter of LB agar. Okay. Now, knowing what to convert the units to just comes with experience. You might be in a lab, and let's say you make a statement that, oh, that's 0.04 grams per mil. Your colleague might be like, oh, what? What is that in normal speak? And you might need to do the conversion to 40 grams per liter. But this is just a part of working in a lab and getting used to the language that's often used. Now, one thing just to quickly note, remember that liters is a base unit, and grams is a base unit. So it's pretty safe to say that if you show the concentration using base units like grams per liter, you can't really go wrong. I think that's going to be a very commonly used volume concentration unit. All right, so we're going to do a more intense practical calculation. You might want to pause for a second and reflect on what we just went through. We're going to do a little bit more math here to reinforce that. And so feel free to pause for a moment and then hop right back on and join us. All right, so this practical calculation is you're in a lab and you need to create some YPD agar plates. Yeast peptone dextrose agar plates are often used for growing lab yeast in a similar way to LB agar plates that are used to grow E. coli bacteria, right? So it's just another kind of growth media plate, okay, YPD. When you look at the instructions from the manufacturer, you see that 80 grams per liter YPD agar powder in water is needed. Okay, so this is the mass concentration that you need to achieve to make good YPD agar plates. Now, you need to make 30 10 centimeter petri dishes for your experiments, right? So that's, you need to make 30 petri dishes of the 10 centimeter diameter plates. And each petri dish needs about 20 mils of YPD agar. Okay? And so there's a little side hint here. We're not doing a simple calculation like just dissolving it into a liter of water. It's a little more tricky here. Okay? So the question here is, how much YPD powder and how much water do you need? Right? So feel free to pause and do the calculation yourself and then rejoin and see if you got it right. You probably did. Or you can just join along and we'll continue to solve this together. Okay, so here is a very useful equation. So you know we've been talking about C equals M over V. What you can do is you can do a concentration equivalence where essentially you can say, let's say I want the concentration 1 to equal concentration 2, but maybe you've got slightly different mass or volume. And so you want to figure out how much mass you might need to add to a different volume than you have in, let's say, another concentration. Okay, and so what you can do is you can substitute the second half, so the M1 over V1, or the M over V for the C, and you could do that on both sides, where instead of saying C1 equals C2, you say M1 over V1 equals M2 over V2. Okay, and you'll see where we're going with this. So we know that we need 80 grams per liter YPD agar. So that's the concentration. So we could actually plug that in. So we could say our mass 1 is 80 grams, our volume 1 is 1 liter. Okay, so we'll plug that in a little while here. M2, or let's jump to V2 here. So we're not making 1 liter worth, right? But we know that's the concentration. We could do a quick calculation to see what the volume we need is, and therefore we can determine the mass. So here we see we need 30 petri dishes, each of which need about 20 milliliters of YPD agar. So that means we need about 30 times 20 is 600 milliliters of total volume of agar, or we could say approximately 600 milliliters of water. Okay, so what we can do is now we know V2 here, so the only missing value we have is M2, and so we can actually solve for that, and we'll go through that in order to know how much mass do we need to add to 600 milliliters of water in order to get our desired final concentration of 80 grams per liter. So we can rearrange this equation, M1 over V1 equals M2 over V2, to solve for M2. And we simply do this by multiplying both sides by V2. That negates this V2, but then we have a multiplication of this term here with V2. Okay, so M2 equals M1 over V1 multiplied by V2. If we plug this all in, we can see we have 80 grams over 1 liter multiplied by 0.6 liters equals 48 grams of YPD agar in 600 milliliters of water. That's going to give us 80 grams per liter concentration. Okay? So this is the sort of equation and the sort of practical computation you'd be doing in a lab all the time. This is a very, very useful equation, okay? This M1 over V1 equals M2 over V2, okay? Very important. Okay, so that's mass concentration. It's fairly straightforward because it's literally a mass such as grams over a volume such as liters, and manipulating that those numbers to maybe get a different mass for a different volume that you can practically use in the lab. So there is an activity that you can jump to now to practice your know-how of mass concentrations, where you're going to use a recipe found online to calculate how much of certain components you need to make some LB agar plates. Okay, so now we're on to the fourth concentration type, molar concentrations. Okay, and this is by far the most complex of concentrations. So let's take this slow and start from the basics. You might have seen some of these principles and some of this information in chemistry class, maybe physics or maybe math. You might have seen it around in various places. And so hopefully we can bring that together and make it of use to you in a lab, because molar concentrations, I would say, are probably the most widely used concentration type used in labs. Okay, so yeah, molar concentration. So let's start out by looking at what is a mole. All right, and there's a little mistake here. This should be a small n, not a big N. Apologies for that. But a mole is a unit amount of a substance. So in the same way that grams is a unit of mass, a mole is a unit of substance. Okay, and the unit, it goes something like this. So this is a very large number. A mole is 6, we'll just say 6 times 10 to the 23. That's a very big number of elementary entities. Okay, so this could be lots of different things. It could be atoms, it could be molecules, it could be electrons, right? So a mole is this number of a certain entity. Okay, and of course today we're going to be talking about molecules a lot, because that's what's used in biology mostly. And so yeah, it's a pretty interesting unit of measure. It's also called, this number here is also called Avogadro's number. So we might see that pop up in a few slides. Okay, this is it written out. So just a giant number of elemental entities per mole. Okay, so again, this could be like 1 mole of carbon atoms, for example, would have this many carbon atoms in it. Okay, so in a way it's kind of simple. We're not going to go into why this number too deeply, or the experiments that were used to derive it, but in short, the way that scientists came up with this number was by doing experiments on carbon 12 grams of carbon 12 have this number of carbon atoms. Okay, so 12 grams of carbon 12 has Avogadro's number of atoms. Okay, so I'm just going to pop up an equation here on the right. That's pretty important. So the equation is n, small n, and again, apologies, there should be a small n here. is moles equals mass in grams over big M, which is molecular weight, which the units are grams per mole. Okay. Do you remember seeing this anywhere, this unit of measure? You might have seen this pop up in chemistry class. Perhaps when you were learning about the periodic table of elements, right? So yeah, an important part of understanding and calculating a mole is the molecular, or I guess in this case, atomic weight of the chemical elements, right? So each atom has a different mass or molecular weight, and that is in the units of grams per mole. All right. So let's do an example here where we look at a molecule. So molecules have molecular weights because they have their molecules, not atoms. And in fact, molecular weights are the sum of atomic weights of the atoms within that molecule. Okay. And so let's look at what the molecular weight of this molecule here, which is glucose. Okay. And so the way you do it is you literally count the atoms that are there and you multiply those by the atomic weights. Okay. And so there's no atomic weights in this simplified version of the periodic table, but you'll find atomic weights usually in the top right corner or somewhere within the square, okay? And so, for example, hydrogen has an atomic weight of 1.01 grams per mole. Carbon has an atomic weight of 12.01 grams per mole. Oxygen has an atomic weight of 16.00 grams per mole, okay? And so what we do is we can count here. We've got 6 carbons, so we could go 6 times 12.01. Again, this is the molecular weight of carbon, equals 72.06 grams per mole. We do the same with hydrogens, 12 hydrogens, so 12 times 1.01 is 12.12, and then 6 oxygens at 16 grams per mole gives us 96. When we add that all up, the total molecular weight of glucose, when we add the molecular weight of all the carbons, hydrogens, and oxygens, is 180.18 grams per mole. Okay? And I have a little note down here, molecular weights, molecular mass. So again, weights are a little bit outdated. Molecular mass is also widely used. Okay, so continuing down this road here, so we just found that sugar glucose has a molecular weight of 180.18 grams per mole, right? And so we could ask the question, what is a mole of, how much does 1 mole of sugar glucose weigh? Well, the answer is simple. It would be 180.18 grams per mole, right? So we could do another fun calculation. How many sugar cubes are in 180 grams of sugar? It turns out it's about 45 sugar cubes, right? Each sugar cube is about 4 grams. So if you're ever in the store and you see 45 sugar cubes, you know that's roughly about a mole of sugar, right? Another way to say it is, if we take Avogadro's number here, we could say that there are this many, Avogadro's number, of glucose molecules in 45 sugar cubes, right? So that's a lot of glucose molecules in those 45 sugar cubes, isn't it? That's an enormous number. Enormous. Okay, so now that we have a pretty good handle on molecular weights, what a mole is, Avogadro's number, let's now look at molar concentrations, okay? So A molar concentration is Avogadro's number of elementary entities per liter. Okay? So we learned about mass concentration, which was grams, for example, of mass per liter. In this case, it's the number of elementary entities per liter. Okay? And so if we look on the right here, I'll show you another equation. So in this case, we have C, which stands for molar concentration, which is in moles per liter. Okay, so again, this is a mole, right? 1 mole per liter. So when we look at the molar concentration, we're looking at moles per liter. And unfortunately, there's no way to really separate C from mass concentration and molar concentration. It's just interchangeably used, okay? So you just need to know the context. If you see a C, a big C, then that designates concentration, and you just need to kind of look at the numbers to understand, or the units to know which system you're working with, whether you're working with mass concentration or molar concentration, okay? So again, molar concentration in moles per liter. We learned about moles, small n, all right, in moles, just MOL, and then big V volume is in liters. So we've got moles per liter, moles over liter. Okay. Now, we're going to quickly learn what I call the handiest equation for molar concentrations. And practically speaking, in the lab, this is the equation that you use 99% of the time. Okay, I don't think I've used these equations in years and years and years. So the way it works is we take these two useful equations, the one we just learned where we have molar concentration equals moles over volume, and we take this one we talked about just a few minutes ago where we have moles equals mass over molecular weight, and we merge those together. Essentially, we can, for this n here on the left, we can replace it with the small m over big M. Okay, so we replace it, and what we're left with here after the substitution is C equals small m mass over big M molecular weight times volume. Okay, and so this is a very, very, very handy equation, as you'll see. Okay, so we're going to do a practical calculation here to get going, and this calculation involves being in the lab, and you need to make 500 milliliters of a 1 molar sodium chloride salt solution. Okay, now I'm going to start out by making a point here that this M, which stands for molar, is molar concentration. Okay, so basically that means that's 1 mole per liter. Okay, so that's an important starting point. And so we could ask ourselves in practical terms, what are we being asked? So we're being asked to create 1 mole per liter solution of sodium chloride salt in water, but we're not looking to do this in 1 liter. Rather, we need 500 milliliters of it. Okay, and there's a little hint here. We're going to use our very handy equation, C equals M over MV. So we know our concentration is 1 mole per liter. Again, that's what this big M stands for, is molar. We know the molecular weight of sodium chloride. We can go to a periodic table and we can add up the atomic weight of sodium and the atomic weight of chloride, and we can add those together and we get 58.44. And then we know the volume we need is 500 milliliters, but remember we have to do this in liters, so we're going to remove the prefix here, take it to the base unit of liters. So that's 0.5 liters. Now we can rearrange this equation a little bit. So essentially we're multiplying this side by big M, big V, and we're multiplying this side by big M, big V, which eliminates it from this denominator and gives us M equals CMV. We can compute this through. So we've got 1 mole per liter multiplied by 58.44 grams per mole multiplied by 0.5 liters. And that gives us a mass of 29.22 grams of sodium chloride salt. Needs to be dissolved into 500 milliliters of water or so to create a 500 milliliter 1 molar salt solution. Okay. And from this, you could also calculate how many molecules are there, right? Using Avogadro's number, similar to how we did it with the sugar, right? So, yeah, so why are molar concentrations useful? Again, rather than using mass, we're looking at the number of molecules per unit volume. Okay. And so while we're not saying, here we have a 1 molar solution, we're not really so interested about the specific number of molecules there. So for example, in this, we'll say 1 Avogadro's, it's half a liter. So it'd be half of Avogadro's number, right? So about 3 times 10 to the 23 molecules of salt in there, or I guess it's sodium chloride, right? So it's not so much at the specific number that scientists are concerned about. Rather, it's the ratio of molecules. Okay, so let's say you have a 1 molar solution of sodium chloride, and in that same solution, you also have a 1 molar concentration of magnesium chloride. Right? So by them both being 1 molar, you actually know that they have an equivalent number of atoms in there of sodium and magnesium. They are in similar numbers. Okay? So that's one of the most useful parts of molar concentrations is being able to work with stoichiometric ratios of molecules. Okay? So yeah, molar concentrations, if you're a pro in the lab, you definitely know molar concentrations. They come up almost every day as well, if not every day in the lab. So understanding molar concentrations is important. So there are a number of activities available to you where you can practice calculating molecular weights / masses, calculating the mass of a substance to get a certain amount of moles, calculating molar concentrations, and converting measures and matching up unit prefixes. Okay, so you can pause now if you like to do those activities, or you can carry along with into the last here, which is the dilution concentration. Okay, so this is the 5th way to describe concentrations in a lab. This one is quite simple. The general principle is often in labs, we create a stock concentration of something, and a stock concentration is a high concentration solution that you need to dilute in order to achieve the proper concentration in an experiment, which is called the working concentration. Okay, and so just the second definition here, a working concentration is the concentration of a substance that is correct for an experiment. Okay, and so the reason this is often done in a lab is to save time. So you can create a highly concentrated solution and put just a small amount of it into your experiment within a larger volume, and put it back in the freezer, and you can use that again and put it back. And it's just a very handy way to manage a lab, more or less. So just as an example below here, It's common in a lab to prepare a stock solution that is 1,000 times concentrated. And so again, this means that you have 1,000 times more, we'll say mass, or it could be number of molecules in a solution than you actually need for your experiment. So in order to get to the correct concentration for your experiment, you add your stock solution at 1/1000th of the final volume. All right. And so just to have a real world example here, let's say you want to create some LB agar plates with ampicillin in them. So in this case, you could create a solution of ampicillin that is 1,000 times more concentrated than you need in your LB agar. And a real example is you might create a solution of ampicillin that's 100 milligrams per mil. Right? And then you might store that in the freezer and pull it out as you need it. Okay. Now, when you want to actually use it, let's say you want to make 100 milliliters of LB agar for your Petri dishes, you would simply add 100 microliters of your stock solution. Note that this is 1,000 times smaller than this, right? So 100 microliters is 1,000 times smaller than the final volume you want, right? And so when you do this, this will dilute your 1,000 times concentration down to 1, right? And you'll actually get the proper concentration you need in that experiment, which is 100 micrograms per mil within the actual LB agar. Okay, so again, you're adding 1,000 times less of your concentrated stock solution, but it's 1,000 times more concentrated, which gets you to the 1x concentration that you need. Okay, so it's as simple as that, and you can have a 5x stock solution, a 50x stock solution, a 25x stock solution. It really depends on what that solution is. There's lots of different examples where this is used in a lab, and it's again just a handy way where you can create a bunch of stock solution and use that for months by just taking it out and adding a little bit of it into your experiment.